Okay, so in this video, I'm going to be telling you about a math problem that has currently, as of early May 2023, a $5,000 prize attached to it. So there is a bounty, prizes for matrix completion problems, and there's some specific problems about matrix completion that if you solve them, these people will give you $5,000. So these people are from the AI alignment community, and they think this problem might be related to making sure that AI systems in the future are aligned with what humans want and are safe for us to use. So it's an exciting thing. If you actually read the problem on this page, it is just about matrices and maybe looks a little bit like pure math dry. Fill in the numbers in this matrix in a certain way. But it's actually related to one of my absolutely favorite problems in statistics, which is why I made this video, to try to show you that problem and the connection. So let's start. Here is the problem I'm talking about. Given three random variables x, y, z, so that what? They're going to have some conditions. They have these three properties. X and y are correlated. That's one property. Let's call these properties 1, 2. 1, x and y are correlated. Maybe to be extra specific, they're positively correlated. And 2, y and z are positively correlated. Okay, so x's and y are correlated. If you calculate the correlation, it's a positive number. They go together, right? Y and z are also positively correlated. They go together. Question. Is it true that x and z must be correlated? So given that x and y are correlated and y and z are correlated, is it true that x and z are correlated? Another way to say this is correlation transitive? X is correlated to y is correlated to z. Is it true that x is correlated to z? That is the question. And to start with, I'm going to do a little example here. My example is all the way down at the bottom of the page here. Example, and this is an example that I made where x is going to be the number of quarters in your pocket. Actually, more specifically, let's imagine we look in your pocket and we see some combination of quarters and pennies. So I did quarters and pennies. Let's let x be the random variable, which is the number of quarters in your pocket. We're going to let y be the total dollar amount of money in your pocket. So from your quarters and pennies. And we're going to let z be the number of pennies in your pocket. Okay. So this is the example I'm thinking of, and we're going to use this example to investigate the truth or falseness of this question. So given that x and y are positively correlated, so the number of quarters in your pocket is correlated with the total dollar amount in your pocket, that is a reasonable sounding statement. Y and z are correlated. The total dollar amount in your pocket is correlated with the number of pennies in your pocket. More pennies, more dollars. Is it true, and maybe I should specify, is it necessarily true? Is it necessarily true that x and z must be correlated? And I will let you think about it, and then I will reveal the answer. So pause the video here and think, and then I will tell you the answer. And the answer, here it comes, answer. So if x, y are correlated and y, z correlated, is it necessarily true that x and z are correlated? And the answer is no, not necessarily. So it could be that x and z are correlated, or it could be that they're not. Let's see some examples. So here is the examples I came up with, and I made them in a nice little Excel spreadsheet. And here is situation 1. This I call the rich versus poor situation, and this is what I think most people think of. And this would be the kind of situation that pops into your mind, which is that you're either kind of more rich or more poor. And when you're more rich, you have more quarters and you have more dollars and you have more pennies. So all three of these quantities, the number of quarters, the number of dollars, and the number of pennies, they all go together. And so in this situation, you either have $1, $2, $5, or $10 in your pocket. So imagine there's 4 different people, a rich person with $10, a poor person with only $1. And in all situations, the people who have more money also have more of both types of coins. And in this situation, if you calculate the correlations, the quarters and the dollars, that's x and y, the first two columns, are correlated with a perfect correlation of 100%. Up to rounding errors. Y and Z, the pennies and the total dollars, are correlated with correlation 99%. And it turns out that if you calculate the correlation between number of quarters and number of pennies, it's 97%. So very highly correlated. This is what most people have in mind. And this kind of thinking is what leads to thinking that, correlation is probably transitive. If X and Y are correlated, they kind of go together, and Y and Z are correlated, they kind of go together. There's kind of like one force driving all of X, Y, and Z, and when that increases, it increases all of X, Y, and Z. So all of X, Y, and Z, any pair of them should be positively correlated. So that is a common way of thinking, but unfortunately, it is not always true. Not always true. And here is the example where it's not always true. So in this example, it was true, but here is a perfectly valid situation number 2, which is that the quarters and pennies could just be plainly independent. So I have 4 columns here. And if you look carefully, 4 rows rather, I have, for the number of quarters, it's either 4 or 0. And half the time you have 4 quarters and half the time you have 0 quarters. And for the number of pennies, half the time you have 0 pennies and half the time you have 100 pennies. And it's set up perfectly so that the pennies and the quarters are perfectly independent. So you can imagine you get up in the morning and you have a bowl of quarters at your front door and a bowl of pennies. And you decide, am I going to bring any quarters with me in my pocket today? And you decide either yes or no. If you decide yes, you bring 4 quarters with you, put them in the pocket. If you decide no, you don't take any quarters. And then you turn to the bowl of pennies and you do the same exact yes or no, completely independently. So you say, am I going to bring pennies with me? Yes or no? If yes, you bring 100 pennies. If no, you bring 0 pennies. So you had 2 choices, bring pennies, bring quarters. And that leads to 4 possible outcomes. And the pennies and the quarters are perfectly independent. They have nothing to do with each other. But both of them are positively correlated with the total dollars you have. So if you bring more quarters, your dollar amount goes up. If you bring more pennies, your dollar amount also goes up. You can either have 1, 0, 2, or $1 from these outcomes. If you bring both pennies and quarters, you can have $2 with you. If you bring one of them, you'll have $1. If you bring neither of them, you'll have $0. So the total dollars, Y, is correlated with both X and Z, but X and Z are completely uncorrelated. They're completely independent. So this is a situation where even though X and Y are correlated, coming back to the general setup, even though in general X and Y are positively correlated, Y and Z are positively correlated, is it true that X and Z must be correlated? No, they could be completely independent. And this is a great example of that. That's one of my favorite problems in stats. We're almost at the matrix completion, but not quite yet. Here is a follow-up question. I've done an example where they're positively correlated. X and Z are positively correlated. That's kind of the routine way of thinking. I've done an example where they're completely independent. Could they be negatively correlated? So follow-up question, is it necessarily true that they're correlated? We saw that the answer was no. No, right? Is it, oh boy, that is a bad spelling of necessarily. Let's delete that. Is it true that X and Z are correlated? No. Follow-up question, could it even be that X and Z are negatively correlated, right? So we saw that it could be positive, it could be 0. Could it even be negative? Is there a way that X and Y can be positively correlated, Y and Z can still be positively correlated, so all positive correlations going on, but somehow X and Z are negatively correlated? And so once again, we're going to do this example with quarters and pennies and money. So think to yourself, do you think it's possible to arrange a kind of a situation with quarters and dollars and pennies in your pocket where the number of quarters and the number of pennies in your pocket are negatively correlated, but they're both positively correlated with the amount of money in your pocket? So I'll let you think for a second and I'll spoil the answer. Could it even be that X and Z are negatively correlated? The answer is yes, it could be. And here is the example, and it's actually not such a complicated situation. Situation number 3, we're making change in either all pennies or all quarters. So we start the day with either $1 or $100 in total money. So imagine you go downstairs at the beginning of the day and you either decide I'm going to bring $100 with me today or $1 with me. And you take that money either all in quarters or all in pennies. And you just decide that independently of the amount of money you have. And if you do that, you'll either have $1 either all in quarters or all in pennies, or you'll have $100 all in quarters or all in pennies. And if you look at the correlations, you'll see that quarters and total dollars and pennies and total dollars, so the correlation between X and Y, or the correlation between Y and Z, these are both very positively correlated, right? If you have a lot of money, if you have $100, you're more likely to have a lot of pennies. Okay, sometimes you'll have 0 pennies when you have $100, but you're more likely to have a lot of pennies with you. So there's a positive correlation there, and the same exact positive correlation exists on the quarter side, right? It's actually the same thing from the point of view of correlation. So big positive correlation between the amount of money you have and the number of either type of coin. But if you look at the correlation between number of quarters and number of pennies, it is a negative correlation. It is a negative correlation. And that is because if you have any quarters with you at all, you definitely have 0 pennies. So if you have quarters, that means you didn't take the pennies. And so you definitely have very few pennies. So sort of the more quarters you have, the more sure you can be that you have very few pennies. And so there's a negative correlation. So not only is it true that this transitive thing doesn't work kind of the intuitive way, if X and Y are positively correlated and Y and Z are positively correlated, not only is it true that X and Z, the transitive thing, is not positively correlated, it could even be negatively correlated. It could even be negative correlated. Okay, what does this have to do with matrix completion? This brings me to the first actual problem, which is like a problem from that $5,000 prize, which is to answer the question quantitatively, what are the minimum and maximum possible values for the correlation? So if the correlation between X and Y is given, and the correlation between Y and Z is given, what are the minimum and maximum possible values for the correlation of X and Z? Not the cough, the correlation between X and Z. So what are the minimum and maximum possible values? Why is this a matrix completion problem? Because you can write these correlations down in a very nice matrix. So another way to say it is to use a nice matrix that looks like this. So let me insert a little 3x3 matrix. Here we go, 3x3 matrix. And let me put some nice square brackets around it. Okay. This you could think of as the correlation or the covariance matrix of the random variables X, Y, Z is a 3x3 matrix, and it has, as its entries, these correlations. On the diagonal, you put the correlation with the things with itself, or the covariance with the things with themselves, and that I'm going to assume is 1. So the correlation is definitely 1. Let's just call this correlation to avoid confusion. So the correlation of X with itself is 1, the correlation of Y with itself is 1, and the correlation of Z with itself, or Z with itself, is 1. The correlation of X and Y could go here on these entries. The correlation of Y and X. Of course, it's a symmetric matrix because the correlation of X and Y and the correlation of Y and X are the same. And the correlation of Y and Z goes on these things, Y and Z. And the question is, what possible values can live in these corners of the matrix? So it's a matrix completion problem. Given some of these entries for correlations, can you figure out what are the possible values in these question mark spaces? And I just showed you that really it's kind of counterintuitive what could be there. So even if the correlations are very positive, what can you put there? And to be very specific, there's a very nice arXiv paper, which is written by the guys who made the prize. So Paul Cristiano, he has this nice arXiv paper, which I opened, and they do this example in their paper where the correlations between X and Y and the correlation between Y and Z are 0.9. So all the variables are unit variance 1, and their correlations are 0.9. So they put in 0.9s everywhere. And the question is, what can you put in? What can you put in here? So example, if they're 0.9 and 0.9 everywhere, what can you do? And so the 5K bounty, which is the problem I mentioned at the beginning, is kind of a high dimensional version of this. So in general, if you have an n by n matrix corresponding to n random variables, not just 3 like we have here, and I give you some of the correlations, I tell you some of the entries, can you figure out what are the possible values in the other ones? And I think they even have a softer version, which is just to say, are there any possible values that you can fill in this matrix to make it make sense? So that's the problem, and it's about matrix completion, but it's actually about random variables and what are their possible correlations. That is the reason it's related to AI alignment, is because when we have AI systems reasoning about things, we want them to figure out, based on the information I have, what is a possible like outcome of the universe and what is not. So if we tell the AI some data about how X and Y depend on each other, and we tell the computer about how Y and Z depend on each other, the computer should be able to reason about what are the possible ways that X and Z should relate to each other. And with only 3 variables, it's not so exciting. But in this nice paper, they talk about systems that have many variables. So if I zoom out a bit, let me see if I can find one of these nice pictures in this paper. So here's one of an AI system that is kind of reasoning about many aspects of the universe by combining what it knows about different variables together. Okay, so figuring out how to do that is an AI alignment question. In the rest of the video, I am going to present to you the solution to this problem for the 3 variable case. So we have X and Y, Y and Z. There is a very nice definitive answer for what are the possible values for the correlation between X and Z. And it's a very beautiful, nice geometric picture. And the reason it's so nice is because this problem, even though it looks like it's about statistics and random variables, is actually secretly a linear algebra problem. And I'm going to write up another problem here. So let X, Y, and Z be vectors in a vector space. In a vector space. Think of them as vectors. And suppose you're given the inner products of X and Y and Y and Z are given. What are the possible values for the inner product X and Z? And to make things a little simpler, let's pretend they're unit vectors. Unit vectors, so vectors of length 1. This is, again, the size of the vector is the variance of the random variable. So the correspondence between problem 3, which is about random variables, and problem 4, which is about vectors, is you can just think of the space of random variables is a vector space, and this operation of doing the covariance is a type of inner product on that vector space. So this is the magic of linear algebra, is that anything that has the rules for linear algebra, you can pretend is a linear algebra problem, and you can solve it there. And what is so nice about linear algebra is that you can draw a picture. So this question, problem 4, you can reason about the answer with just one picture, and you will know the answer to this question, what are the possible correlations, in 1 second. And then to prove it is a little bit longer and will involve the quadratic equation, but it's still very elementary. So here is my picture proof. Let me see if I can open up a picture. So we have 3 vectors, X, Y, and Z. They are vectors. And the correlations X, Y is given to us. Let's call that rho of X, Y. And the correlation Y and Z is given to us. Let's call that rho of Y, Z. And the question, what could the inner product of Y and Z, which I'm going to call rho of Y, Z. No, not rho of Y, Z. Rho of X, Z. What could that be? X, Z. X, Z equals question mark. What is possible? What are the minimum and maximum values? And again, these are vectors, so you can draw them. Let's draw X as a nice vector over here, and Y as a nice vector over here. Let's do it in purple. And the nice thing about X and Y, if you draw 2 vectors, let's say they're unit vectors. Let's make this one a little bit shorter. If you have 2 unit vectors and you want to visualize where is the correlation, where is the inner product, the dot product in this picture, the dot product appears to do with the angle between them. So if you look at this angle between these 2 guys, that angle, I'm going to call that theta xy, the angle between X and Y. And that appears in the following relationship. The correlation is the cosine of the angle of theta xy. So the inner product is the cosine of the angle. And your brain is very good at dealing with arrows and pictures and angles. And you can translate all of that goodness into the correlations through just the fact that the cosine of the angle is exactly the correlation you're looking for. Okay, so that was the angle between X and Y. What about the angle between Y and Z? Let's do that over here in red. Here is Z. And here's the angle theta YZ, which is the cosine of theta YZ is the thing we're interested in, is the inner product or the dot product. And that's because they're unit vectors. And now we can ask, what could the possible inner product between x and z be? That's the same as asking the question, what is the inner product? What is the cosine? This is the cosine of the angle theta x to z, right? So we take this big angle, theta x to z, and we're asking what are the possible cosines? An even better question, like what are the possible angles? And from the picture, I think you can see, like very visually speaking, it's very easy to see what the possible angles are. So what are the possible values? Possible values for theta x z. What are the possible values? I just drew one of them. One possibility is that theta xz equals the sum of the other two angles. It's theta xy plus theta of yz. This is one possibility. Possible. Another possibility is that they could subtract. So here's a picture with x over here and y in the middle variable over here, and then z on this side. So this is another possibility. And in this one, the angle between z and x, theta x to z, and the angle from x to theta x to y, and theta y to z, theta y to z, they are subtracting instead of adding. So in this situation, theta xz equals the difference theta xy minus theta of yz. And that could happen too. So this is another possibility. And your intuition should be, well, in 2 dimensions, this is really the only thing that can happen. But if you're in a higher dimensional space, the vector z, or the vector z, can sort of live out of the page and sort of take on anything in the circle that goes around at the angle theta yz. And so it can be any of the angles in between. So as an intuitive answer, all the possible angles are everything in between these two extremes. So the intuitive answer is that theta between x and z has to be between these two extremes of perfectly adding and perfectly subtracting. And this is, it turns out, and I'm going to show with some very simple, like actual math, culminating in the use of the quadratic formula, that this is actually the true answer. That the only angle between x and z, it can be all the way up to this at the most and this at the least. And it's a very nice, satisfying answer. Before I show you the answer, let me show you the picture of the 3 situations we had for the quarters. So just to understand the things. So we had situation 1. We had our 3 situations. Can I zoom in anymore? Maybe not. Okay, we're going to do it like this. So situation 1. And that was rich versus poor. And all 3 were positively correlated. All positively correlated. And this is the situation where the 3 vectors sort of line up like this. So there's x, and there's y, and there is z, and they are all lining up very close together. So that was the situation where the correlation between x and y is quite large. The correlation between y and z is quite large. And the correlation between x and z is also quite large. And it looks like this. Let me show that spreadsheet one more time for people who are looking at that. So the correlation between x and y was 1. The angle was so close to 0, the cosine is almost 1. And the correlation between y and z is also extremely close to 1. And then when the correlation is extremely close to 1, the angle is close to 0. And the correlation between quarters and pennies between x and z is a little bit further from 1. The angle is a little bit larger. And it really is exactly this picture of the 3 vectors lining up. And I think the thing to remember is that small angle, this means big correlation. Right? Because the angle theta is related to the correlation is the cosine of theta. So when theta equals 0, the cosine of 0 is 1. You have a really big correlation, the biggest possible correlation. When theta is pi by 2, 90 degrees, pi by 2. 0 angle goes to correlation equals 1. And pi by 2 angle goes to correlation equals 0. And now you're appreciating why I like to type things when I can, because my handwriting is quite messy. And in between is in between. So in this situation, the correlation between x and y is extremely high. The correlation between y and z is also extremely high. The correlation between x and z, the two outside guys, is a little bit lower than the other two, but is still very positive. And that was situation 1. Situation 2, and this is the situation where the x and the z were completely independent, looks like this. So here's x, here is z, and the vector y is exactly in between them somehow. So this is situation 2, where pennies and quarters are independent. Independent. Okay. The pennies and the quarters are independent. So that was situation 2. And I can illustrate that one over here back in the spreadsheet again. So the pennies and the quarters just have nothing to do with each other, but they are both positively correlated with the total dollars. That is exactly this situation over here, where the x and the z are at 90 degrees to each other, so a correlation of 0. But y is in between them, and therefore these angles are small. Well, they're not super small, but they're smaller than 90 degrees, so you have a positive correlation. Okay. So the theta yz small, and theta xz is small. Well, I guess in this case, you can imagine they're right now, as drawn, they look like they're exactly 45 degrees. And indeed, if you were in 2 dimensions, it would have to be 45 degrees. But you can imagine in 3 dimensions, the vector y can point out of the page. And so you can get angles other than exactly 45 degrees in this situation. Okay, that was situation 2 where they were independent. Last but not least, let's do situation 3. Situation 3. And that was the situation where x and y are positively correlated, y and z are positively correlated, but x and z were negatively correlated. And that one looks like this. So x is here, z is down here, and y is somewhere in the middle, so that the angle between x and y is positive. The angle, or it's less than 90 degrees. This angle is small, theta xy small, theta yz small, and small means less than 90 degrees. As soon as you're less than 90 degrees, the correlation will be positive. But the correlation between x and z, this angle is bigger than 90 degrees. The cosine of that angle is negative. So the cosine of theta xz is less than 0. And that means the two variables, x and z, are negatively correlated. So you can see all the situations that can happen. And intuitively speaking, the worst and the best case are sort of the angles either completely add together or they completely subtract together. Let's try now, for the rest of the video, I'm going to prove this relationship sort of rigorously with some simple math. And this is all a nice linear algebra proof, which is why you should pay attention in linear algebra class, even if it feels boring sometimes, is we are going to work in a basis that is convenient for us. So we're going to choose, so this is the proof of the min and max correlation. And the first step, and this is, I think, the most important step, if you do this step correctly, everything else is a breeze. We're going to choose a convenient orthonormal basis to work in. And in that basis, I'm going to make the vector x, I'm going to make it the vector 1, 0, 0. So in the basis I'm working in, I'm going to pick a basis, I guess. Okay, we're in some vector space. We don't know how many dimensions there are. So technically it's 1, 0, 0, ... Right? So x is the first vector. I'm only ever going to use the first 3 components. So I'm going to write as a shorthand, I'm going to write 1, 0, 0. And you guys are going to have to remember that the rest of the vectors in the vector space will never get touched. I'm only ever going to use the first 3 components of the vectors. And that's because I only have 3 vectors, x, y, and z, to deal with. So, they live in a 3-dimensional space. The span of x, y, z is at most 3-dimensional, and I can just deal with those. But so x is going to be 1 and all zeros. So x is literally the first unit vector. And then the vector y, I am going to write it as something I'm going to call A, something I call B, and then 0, ... So the vector y only has non-zero components in the first 2 entries. And actually, I can tell you exactly what y is. It's going to be the cosine of theta xy and the sine of theta xy. And how do I know it's going to be the cosine and the sine? Because the inner product of x and y is equal to the first component, right? And the first component squared plus the second component squared equals the norm of y squared, which is 1. So I know that y is a unit vector. I know that when I do the inner product with x, which is 1 and all zeros, I have to get the first component back. And solving this equation means that y has to be the vector with theta xy and sine of theta xy. Okay. And I'm working in this is very important. I can choose, because I only have 2 vectors so far, I can choose the convenient orthonormal basis so that it only has components for x and y in the first 2 entries, right? X I chose as the first vector. Y, I said, whatever is in y that is orthogonal to x, whatever the orthogonal projection of y onto x is, make that the second component. So, if you want to be very pedantic, you don't need these details. But the vectors I'm working in, u1 is just x, the first unit vector, and u2, the second vector that I'm doing, is the orthogonal projection of the vector y onto the vector x. And if you want to write this down, it's something like y minus the cosine of x divided by the sine, I think, of... So that normalizes it to be a unit vector. This is the let's say, the normalized projection. If you don't make sense of any of that, just keep in mind x and y only need the first 2 components because of this projection idea. Last but not least, we have our third vector in the problem, which is the vector z. And it would be very nice if you could say z only has a non-zero components in the third component or something. But we have our third vector. It can have a non-zero component in any of its first 3 entries. So writing out what it is, it's going to be something that's non-zero, something that's non-zero, and something that's non-zero. And then it's going to have a whole bunch of other entries we don't care about. We're going to make sure they're all zeros. This is what I mean to say. So when I say the ... all these entries are 0. Everything past the first 3 in all 3 of our vectors is always 0. So there's all zeros down here. You really only have to deal with the first 3 components. Okay. So z is going to have something non-zero in the first 3 components. I'm going to call whatever it has in the first thing, I'm going to call that lowercase x. Whatever it has in the second component, I'm going to call lowercase y. And whatever it has in the third component, I am going to call that the square root of 1 minus x squared minus y squared. And that is because I know z is a unit vector, and so its components have to sum square to 1. And so I can figure out the third component based on the first 2. And again, even though we're living in a high dimensional space, I don't need to worry about any of the other components. They're all 0 in the basis I'm working in. So I'm choosing this nice convenient basis where x, y, and z are essentially vectors in 3 dimensions, because I have 3 of them, and I can just work in this basis to do my problem. And here's the thing. We're trying to answer the question, what are the possible values of x and y? What are the possible values for x and y? What possible values of x and y work? And the possible values of x and y that work, they will give us the correct inner product between y and z. And then once we have the correct inner product between y and z, we can answer the question, what is the inner product between x and z? That is literally looking at x, which is a 1 in all zeros, and looking at z, which has an x in its first component. The inner product between x and z is the lowercase x. So whatever the possible values are for the lowercase x will answer our original question, what are the possible values for the inner product between x and z? Okay, so what are the possible values between x of x and y? Well, we know one thing for sure. Here is condition 1, and I'm running out of space here. Let me erase some of this stuff that is not needed, that is orthogonal to the issue at hand. Okay, let me erase some of these things that I said before that we don't need anymore. This is what we're going to answer. What are the possible values of x and y? Here is one condition that is an easy one. Condition 1. And condition 1 says x squared plus y squared must be less than or equal to 1. X squared plus y squared must be less than or equal to 1. And that is because the third component, you can't take the square root of a negative number, where talking real things here. If x squared plus y squared was greater than 1, then z could not be a unit vector, right? So because it's a unit vector, the first two components on their own can't be larger than 1. That's one condition. And here's the other condition, condition 2. Condition 2 is that the inner product between y and z must be equal to whatever was given. It's equal to the cosine of theta yz. So in the problem, we were given the inner product between x and y, which I already used to make these entries. And we were also given the inner product between y and z, which I haven't used yet, but I'm using now. And I'm using it in this condition that the inner product between y and z must be the cosine of theta yz. Okay. And the inner product between y and z, I can also write out by using my bases. Look, I have this nice, I have both things written out. What is their inner product? I can write it out very simply. It's x times the cosine of theta xy plus y times the sine of theta xy, and that together must give the cosine of theta yz. So this equation is the equation that enforces that the inner product between y and z is the right thing. This equation over here simply enforces that it's a unit vector. And those two conditions, as long as those two conditions are met, I can make a vector z that has everything we need. So these are the only two conditions on y and z. And fortunately for us, in this low dimensional setting, both of these conditions are perfectly able to be visualized. So the first condition, if you think of all the possible x values for lowercase x and lowercase y, you can think of that as the Cartesian plane. And the equation x squared plus y squared less than or equal to 1 is a circle. It's saying, here is the circle, x squared plus y squared equals 1. And we're saying you have to live somewhere inside that circle. So the possible values of lowercase x and lowercase y, they must be somewhere inside that circle. What is the orange equation saying? It is a line. This is the equation of a line. And x times something that we're given plus y times something that we're given equals something else we're given. This is the equation of a line. So this equation is simply some line that lives through here. So it's some line. This is the line that enforces yz equals cos theta yz. So given the cosine that you have some line. And so what are the possible x and y values? They're all the possible points that are on the line and also in the circle. So the solution is some line segment that looks like this between these two things. That's it. That's going to be the answer. The answer is going to be the set of points in the interior of the circle between these 2 points. And if we can solve for what are these 2 points at the end, then we will have the solution. And I visualize this in Desmos for you because I love Desmos. So here it is. Here it is. So here is the unit circle, x squared plus y squared less than or equal to 1. And this is why I called them lowercase x and lowercase y, so that I could plot them in Desmos. And I have the equation x times the cosine of theta xy plus y times the sine of theta xy equals the cosine of theta yz. And let me plot that line for you here. It is what I'm plotting here as a green line. Let's make it red so it matches what I drew a second ago. And I guess let's make this yellow. Oh, we don't have yellow. Okay, we're going to go with blue. So there we go. That's it. It's a line and a circle. And I made it so you can slide these things around and you can see what happens. So if theta yz is 0, then as you slide theta xy around, you get this nice situation of always being on the rim of the circle. And as you increase theta yz, you kind of get closer towards the center. But the slope of this thing is also always related to the angle theta. So it's a very nice geometrical situation. And you can try to figure out geometrically what happens. I'm not good enough at trigonometry to do it geometrically, so I'm going to do it algebraically to find the solutions. I'm going to try to solve for these 2 points. These 2 points on the end. And these 2 points on the end are the solution to these two equations. X squared plus y squared equals 1. So on the edge here, it's x squared plus y squared equals 1. So if you solve for x squared plus y squared equals 1 and simultaneously x times the cosine of theta xy plus y times the sine of theta xy equals the cosine of theta yz, you get a quadratic equation. So you get the solution, solve, and the equation you get is x squared plus, writing everything for the variable y, you get cosine of theta yz minus minus x times the cosine of theta xy divided by the sine of theta xy all squared equals 1. So if you take the second equation and you use it to eliminate the variable y, and you plug that into x squared plus y squared equals 1, you get this equation. And this is a quadratic equation for the variable x. And I've even plotted the quadratic equation over here in Desmos. That is this line over here. It's a quadratic equation, and I just wrote all of that stuff, and I took the 1, I said instead of saying equals 1, I moved the 1 to the other side as a minus 1. So we're looking for the roots of this equation. And the roots of this equation are exactly the x values of our interval. Exactly the x values of our interval. So if I put this equals 0, Desmos will show you that the solutions are exactly what we want. The solutions to this quadratic equation are exactly the intervals we want. Okay, so how do we solve a quadratic equation? We use the quadratic formula. So if you take this guy, this is a quadratic equation, its coefficients involve cosine of theta xy, sine of theta xy, and you do the quadratic formula. Let me show you what you get. So you do the quadratic equation, the quadratic equation. You're going to get the following. You're going to get the sine of theta xy times the sine of theta yz. And this part is the, in the quadratic equation, it's minus b plus or minus the square root of b squared minus 4ac all over 2a. This part is all this. The minus b over 2a turns out to be the sine of theta xy times the sine of theta yz. Very nice. There's when you have to do this, you do end up with like a square root of 1 minus cos squared, so you do have to use some trig identities. But that is the minus b over 2a. And then you're going to have a plus minus, and then what you're going to get over here is going to be the square root of b squared minus 4ac all over 2a. That's going to be the plus minus part. And this one really does involve a lot of trig identities. If you do the trig identities correctly, you get the cosine of theta xy times the cosine of theta yz. So this is after trig identities. Okay. And this is the answer. So if you go into Desmos and you plot, okay, I've spoiled the final answer here, but it is the sine times the sine plus or minus the cosine times the cosine. And this is the last trig identity of the whole problem, is to recognize that this formula is exactly the formula for the cosine of theta xy plus or minus theta yz. So the two solutions, the two roots, are actually very simply, they're the sum of the angles and the difference of the angles. So I have it written here. I said, Desmos, please tell me all the x values that are between cosine of theta xy minus theta yz, and please tell me all the x values that are at most theta xy plus theta yz, and that Desmos gives you the nice green region, and that green region is exactly the solution for when you go in between. So no matter how you slide it, it's always that thing. And I will say there is one important value. The actual midpoint is sort of just theta xy. That would be the midpoint. In some sense, that's the midpoint, right? If you take the midpoint inside the cosine, that is the thing. If you take the midpoint outside the cosine, you get a different answer. So if you do x equals cosine of theta xy minus theta yz plus the cosine of theta xy plus theta of yz divided by 2, a whole thing divided by 2. Will you let me do that, Desmos? X equals. So that's the actual midpoint, whereas the cosine of theta xy is the midpoint of the angles, and then you do the cosine, and that is a slightly different thing. So there you go. We've answered the question, what are all the possible values? And I've shown you two different ways to do the midpoint. And the midpoint is actually what this paper is interested in. The title of this paper is Formalizing the Presumption of Independence. And it says if you don't know anything about the variables x and z, and you know about x and y, and you know about y and z, what should we use? What should the default assumption be about the variables x and z? And In the paper they have some different ways to think about it and pros and cons of either of them, but I think it's not a fully thought out problem, fully finished problem, fully solved problem, and that is why there is a big bounty for this kind of problem. Okay, I think I've gone on for long enough. I will stop there, and hopefully you enjoyed it and got something out of it.